Alright, welcome back to day 12 of LeetCode grind. Solve or go home. 30 minutes, solve or go home. Alright, let's see what we got. Partition list, okay. Given the head of a linked list problem. Okay, cool. Given the head of a linked list and a value x, partition it such that all nodes less than x come before nodes greater than or equal to x. You should preserve the original relative order of the nodes in each of the two partitions. Relative order. What the hell? What does that even mean?
So if 4 comes before 3 before, 4 still comes before 3 after.
Yes, but it says partition is such that all nodes less than x.
Yeah, so in the picture in example 1, you're collecting all the gray ones.
Oh, and just popping it up to front. I see.
Yeah.
Oh, okay. So, okay. First thoughts. Just traverse the linked list. Build a map with the where in. Okay, you can build a map with the number and where in the linked list it lies, kind of like an index.
Okay.
And then given that, you just compare it to x, and then whatever is less than whatever's less than x, slide them over, and then the rest you keep them there.
Oh, I see. So you want to extract index and order, or index and value, and put it in the map.
Yeah. So that.
Okay, so that means you would have to rebuild the list from the dictionary afterwards.
Yeah, that's fine, because then we could just initiate new linked lists and then just set up the arrow, the pointers afterwards.
I see.
Is that fine?
I mean, that's a reasonable approach.
So I think another approach I would say in the past to do it is just replace the numbers with Williams that don't do that.
Okay. If this were an interview setting, I don't know if they would be okay with basically getting completely out of the linked list area and then coming back into it afterwards, right?
Yeah. Okay. So yeah, either way. Okay.
So I think it might be more thematic, I guess, to
do it
create like other linked lists that you use to keep track of, the partitions, and then stitch them together at the end, something like that.
Yeah, that works. Okay. So all right. So in that case, I will be okay. So I would iterate through it. Every time I'm iterating, I'm looking at the number. If that number is less than x, then I need to wait, actually no. So x is a number, right? Yeah, it's a number. Okay, so we don't know the position of it yet. Okay, so we check the number. If it's less than x and it's not, and we didn't find x yet, then we don't care, we just keep going. If it's greater than x,
no, it's not about finding a number. It's at every node you say, is it less or is it greater than or equal?
Yeah,
that's it. It belongs to two splits. One of two possible splits. Yes.
Yeah, I guess that's true. Okay, I see what you're saying. Oh, okay, yeah. Okay, so yeah, if I'm going through the example 1, so I'm checking, is 1 greater than or equal to x? It's not, so it doesn't matter. So I go to the next one. Is 4 greater than or equal to x? Yes, it is. So start a new new partition based on this 4, and check 3. 3 is greater than or equal to 3. Yeah, so to keep it there, it's still there. Check 2. 2 is less, so you slot it. You go to the first partition. First partition dot next is 2 now.
Right.
And then 3 dot next is 2 equal to 2 dot next. And then you check the next one. It's 5. So then that is greater. So
I see. So you're doing it in place.
Yeah. Is that what you were saying?
That's actually a little bit more complicated than what I was thinking.
Oh, you were just you're just literally creating 2 new linked lists and then just point.
Correct.
Okay, that's way simpler. That's way simpler. Okay.
And you just append to it depending on.
Oh, okay. Yeah, that's so much simpler. Okay, I think I'll do that. Okay. Okay, so we have the head. Okay, head, if head, then okay, then we check if head dot val greater than or equal to 3. Oh, not 3, it's x. Yeah, so wait, define the front partition. Front partition equals new list node. Is it? Do you declare new in Python? I don't think you do, right?
No, you just make a list node.
Oh, you can just do list.
Yeah.
Okay. And
no new.
Okay.
No. You need to define list node. List node is the object that is given to you in line 2.
Yeah, that's what I'm saying. So, list node.
No, you don't have to say new.
Yeah, that's what. Okay, and okay, when you said just list, I'm like, I thought you meant array. Okay, my bad. All right. Okay, so if head.val is greater than or equal to x, then we put it in the end partition. End partition dot. Okay, wait. So when you do list node initialization, oh, you have to pass in a val and then next, right?
Well, the default value is 0.
Oh, okay.
But you don't care about it, right? Because it's you're gonna return the one after this guy, because this is a dummy one.
What do you mean?
So you're making an empty list node here just so you can
so I can start chaining onto it, right?
Exactly. But then afterwards, when you want to access the actual partition, you take the next value, not the first one.
Oh, I see what you mean. Okay. So it'll be end partition dot next equals
Correct.
head dot head wait, list node head dot val and head dot next.
Oh no! You don't have to define the list node. You can just pass the. Yeah, otherwise you're creating everything. You shouldn't.
You're just setting it to head.
You're rerouting the pointers.
Okay. And else front partition. And next equals head. And then iterate through head. And next equals next. Wait, head dot next equals head equals head dot next.
Okay.
Okay, but so I'm storing these, but these all still have. Oh, I see. Okay, so I'm just building all of these, and then I just have to fix the pointers at the end.
Also, you're doing an if, not a while. So basically, it ends up step 1.
Oh yeah, I was gonna recursively call, but I guess that's bad. Okay, sure. It's not len. What am I doing? While head, yeah, while head. Yeah, because if I do head that next, the last one would be null, and then this should exit the loop. Okay. So if I do this,
right.
What's up?
Okay, but what's wrong here now?
Yeah, I need to get to the next one. Wait, I need a pointer. I need like a dupe. Because if I move through this,
then you're at the very end.
yeah, and then I won't. Yeah, then I can't use it. So I have to make a new var here, another var here to handle this, to handle the process, the moving process of it.
So yes.
So I need like another thing. I need like an partition pointer or something.
You can call it pointer. You can call it whatever you want.
There's end pointer. It goes end partition. Front pointer. Okay, and then it would be Okay, so end partition dot next equals head. That's fine, but then I need to. No, it should be end pointer dot next, and that's, yeah, that should be fine. And then because they're both pointing to this one, as long as this one's traversing this one, at the end will still be the first element, right?
Right.
Okay, and then head goes, that's fine. And then at the end, return front partition. Wait, no, not return. I need to set it up first, so I need to do result. So just do front partition dot next equals end partition dot next. And then just return front partition.
Careful. So what's front partition dot next?
Oh, that would be the starting element, right?
It'd be 1, right? It'd be for the example, you have front partition is dummy 1 to 2.
Yeah.
And end partition dummy 3 before 3 5.
Yeah.
So now front partition dot next, if you assign that, then your 1 2 2 goes away. Right?
Oh, okay. Front partition. We don't want to assign front partition dot next. We want front partitions dot next dot next.
Well, where is your front? Where's the last one of your front right now?
Oh, actually, no. I could just. Okay, I could just set it to the next one, and then set it. Right? If I force it to move to the
then you drop everything from the 2 onwards.
Wait, why?
Oh, print it out.
Okay.
You should print out front partition and end partition.
Okay, I'll do it before and after.
It's gonna be 1 4 3 5 if you do this.
One, 4, 3, 5, yeah. Why does it do that?
So look at front
Oh,
partition.
wait. No. Okay, I got it. It's okay, my bad. It's not this. It is I need to loop to the end of the front partition, and then that one needs to append to the first.
You need to loop to the end of the front partition.
Hmm?
You need to loop.
Well, I don't have access to the tail, do I?
Yeah, you do. Where's the pointer at right now?
Oh, yeah, you're right. We just finished it. Okay, yeah, my bad. Okay. So it's just front partition. Yeah, wait, isn't that what I wrote before? Even though I didn't think it was.
No, you don't deal with front partition. You're dealing with the end of the front partition.
Yeah, because currently no front pointer. Oh my god, I keep mistaking it. Okay, yeah, front pointer dot next equals end partition dot next.
Right, and then what about rear pointer?
Rear pointer is at the end of rear. Is it even? Do we still?
Right, but because that could have happened earlier, it will still have a node possibly, right? So you have to null it out.
Wait, null out end pointer?
Yeah.
Wait, why is that?
Look. you're printing it, right? You can just look at where it prints out pointer or end partition. When you already print it in the results, scroll down. So just look at your standard out.
Yeah, which one am I looking at? The second one or the first one?
Line with the standard out.
Yeah, 0, 1, 2, 2, 0.
Yeah. You see how you have 4, 3, 5, and then a 2 at the end?
4, 3, 5, 2, yeah.
Yeah, where's the 2 coming from? It's because in the original array, 5.
Oh, the 5 still pointing at 2. Oh, you're right. Okay, that makes sense. So at the end of this, you have to clean it out. Okay, end pointer. Next equals none. Okay, let's print. Alright, this one should be in correct order now.
Right, but why did you do end partition next?
Where?
In line 25,
because
end partition.
end partition is a dummy variable, right? So we need the next
right.
part.
And so is front partition. So how do we do that for front partition?
Oh, yes. Yeah, that's why I was printing 0. Okay, that makes sense. 1, 2, 2, 4, 3, 5. Yeah. Okay, that looks good.
Yeah.
Do you have another example?
Yeah.
Oh, we do.
That's basically it.
Yeah. Okay. Just test this one real quick, but yeah, I think it's fine. All right. Cool. Nice. All right.
Yeah, so I think if they made you do it in place, it would be a lot trickier.
Yeah, for sure. Because you have to track everything in the.
But you can still do it.
Yeah.
You know, technically, I guess you wouldn't have a front partition. You would just start with head.
Yeah.
So
No. Yeah. So I think the algorithm is you're looping through. If it's greater or less than, you have to like. Wait, I think you make an end partition. If it's greater than or equal, you put into the end partition. If it's less than, you leave it in place, and then you just change the pointer to point at you. So so currently, like if you're looping, like let's say you're looping through this one, you check 1, right? 1 is less than, so it's fine. Leave it alone. You check 4. Oh, it is greater than. So I'm gonna put this into end partition, and I'm gonna change this one's .next pointer to this one .next, and then keep checking. And then this one is whatchamacallit? This one is greater than. So I'm putting end position, and then I check next one. This one is less than. So this pointer now points to this one instead.
No. It still points at that one, so it's fine. So you have two pointers, one at the beginning of the lowest array and one at the beginning of the greater than array. And then you process nodes, and then if it's less than x, then you shove it to the beginning. Otherwise, you keep the order.
Yeah.
You shove it into the end of the first pointer.
Okay.
But yeah, it's the same principle really. It's just a little bit more tricky.
Yeah, because then you don't get to have these extra bars that just handle it and just like kind of append them together, kind of. But then you have to actually like move around the pointers so they point to the correct things.
Right.
Yeah.
Okay. Very nice.
All right. Thank you. No. Oh, I didn't even time it, but yeah, it's less than. All right, we're good. No going home.
Okay.